Welcome to Science Pills. Usually when we talk about diagnosing a problem or, just understanding any kind of system, there's this baseline expectation of precision.
Right.
Like if you break your arm, the X-ray shows a jagged white line, the doctor just points at it. Broken or not broken.
Exactly.
It's binary, it's clean, and honestly, it's comforting. We really like the world to be visible and easily categorized like that.
Yeah, well, that comfort really just comes from living in a macroscopic world. I mean, we expect cause and effect to be entirely visible.
Right, like pushing a glass off a table.
Exactly. You push it, it falls, it shatters. The rules are reliable. You don't have to guess if the glass is going to fall up.
But, and this is where today's deep dive gets wild, when you zoom in, like really zoom in, when you look at the fundamental building blocks of that glass, or the table, or even, the very neurons in your brain that are processing this conversation right now.
Rules just break down.
Yeah. Suddenly, that reliable X-ray machine is completely broken. You transition from this solid, predictable world into something fuzzy, probabilistic, and honestly deeply weird.
It is weird. It's arguably the ultimate mystery of modern science.
And that transition is exactly what we're tackling today. Because for you, the listener, if you're looking to cut through the noise, our mission today is to answer one of the most profound questions in physics.
Which is basically, how does the universe build a concrete floor out of mathematical ghosts?
Exactly. How does this solid, reliable, classical reality you experience every single day actually emerge from the chaotic, fuzzy probability clouds of the quantum realm?
And to answer this, we've gathered a pretty massive stack of sources for you.
Yeah, we're spanning almost a century of physics here. We've got foundational historical papers from the 1930s on the Einstein-Podolsky-Rosen paradox,
Right.
all the way up to literally cutting-edge research from 2025 and 2026.
Yeah, we are looking at brand new theoretical frameworks, experimental biophysics data, advanced simulations. It's a lot.
It is a lot, but I think what's crucial to establish right away is that this isn't just, abstract math meant for some chalkboard in a university basement.
Oh, absolutely not. This physics is actively happening inside you right now.
Which is insane to think about.
It really is. I mean, we're going to explore how your biological cells utilize quantum tunneling at this exact second just to keep you alive.
We'll also look at how individual atoms are not those hard billiard balls you were taught about in middle school chemistry.
Right. They are actually squishy, compressible objects.
And we're even going to examine a highly provocative new framework from 2026, suggesting that consciousness itself, like the mind, might be the fundamental field of reality.
It's a huge journey today.
Yeah, so to begin this journey, we kind of have to start at the crack in the foundation.
Right.
Because before we can understand how the universe builds our solid reality, we have to understand how quantum mechanics completely broke the classical rules we thought governed everything.
We really have to go back to 1935 for that.
Yeah, to a legendary paper by Albert Einstein, Boris Podolsky, and Nathan Rosen.
Commonly known as the EPR paper.
Right, the EPR paradox.
Mm-hmm.
And the driving force behind this paper was that Einstein was just incredibly frustrated with the leading quantum theory of his day.
He was beyond frustrated. I mean, he thought the theory was fundamentally incomplete.
Because of the whole Copenhagen interpretation thing.
Exactly. At the time, the Copenhagen interpretation, which was championed by Niels Bohr, was really taking hold in the physics community.
Right.
And it essentially argued that a quantum particle doesn't actually have a definite state, like it doesn't have a specific location or momentum until you actually measure it.
Though until you look at it, it's just, what, a math equation?
Pretty much. Until that moment of measurement, it exists as a superposition. It's just a cloud of probabilities.
And Einstein, being a staunch realist, just completely rejected this.
He hated it. He believed the universe had to be deterministic and, most importantly, local.
Okay, let's define local for the listener, because it's kind of the crux of this whole deep dive.
Sure. Local essentially means that an event happening right here, right now, cannot instantly affect an event happening light years across the universe.
Right. Information cannot travel faster than the speed of light. That was the golden rule of Einstein's theory of relativity.
But the mathematics of quantum mechanics predicted this thing called entanglement.
Yes. Entanglement is where things get really messy for Einstein.
Right. Because if two particles interact and become entangled, their properties become mathematically linked.
Exactly. So according to the Copenhagen interpretation, if you take those two entangled particles and separate them by, say, 1,000,000 miles,
Okay.
and then you measure particle A, its probability cloud collapses into a definite state.
Like it picks a spin or a position.
Right. But simultaneously, instantly, particle B, a million miles away, also collapses into a corresponding state.
Which Einstein famously derided as spooky action at a distance.
Yeah, spukhafte Fernwirkung in German. He just flat out refused to believe that particle A was somehow instantly communicating with particle B faster than light. I mean, it violates his life's work.
Exactly. So he argued that there had to be a simpler classical explanation. And that's what the EPR paper was about. It presented a thought experiment to prove that this spooky action was nonsense.
Einstein proposed what became known as hidden variable theory. And our sources use this really great classical analogy to explain Einstein's view here. I think it really helps ground it.
The black and white balls analogy.
Yeah, exactly. So for the listener, imagine two balls, one black, one white. You put them in two separate sealed boxes. I keep one box here on Earth, and I send the other box to Mars.
Okay.
Now, if I open my box on Earth and I see a white ball, I instantly know that the ball in the box on Mars is black.
Right. And notice what didn't happen in that scenario.
What do you mean?
Your white ball didn't send a magical, faster-than-light signal to the Mars ball to tell it to be black.
Oh, right. They were black and white the entire time. The information was always there, just hidden inside the boxes.
Exactly. You just didn't know which was which until you looked.
And Einstein thought quantum particles were just like these balls.
Right. He thought their properties were predetermined from the moment they interacted and separated. Quantum mechanics just wasn't advanced enough yet to see those hidden variables.
So to Einstein, it wasn't spooky action at all. It was just uncovering a pre-existing fact.
Yeah. It's a highly intuitive, very comforting view of the universe. It preserves cause and effect perfectly.
And for what, almost 30 years, it was basically just a philosophical stalemate, right?
Pretty much. Because you couldn't prove whether the particles were communicating instantly or if they just had these hidden variables all along.
Because the outcome looks exactly the same once you open the box.
Exactly. But then, in 1964, a physicist named John S. Bell completely changed the game.
Enter Bell's theorem. This is where it gets crazy.
Yeah. Bell decided to drag this entire debate out of the realm of pure philosophy and into actual testable mathematics.
And the brilliance of Bell's approach, from what the sources highlight, was that he didn't even try to prove quantum mechanics right.
No, he used a logical method called reductio ad absurdum.
Right.
He essentially said, okay, let's assume Einstein is absolutely right. Let's assume the universe is locally real and hidden variables are orchestrating everything behind the scenes.
Okay, so working from Einstein's assumption.
Yes, and working from that assumption, Bell derived a mathematical formula, an inequality.
Bell's inequality.
Right. And it essentially set a strict upper limit on how often the measurements of two separated particles could perfectly correlate with each other, assuming they were just following pre-programmed hidden instructions.
Okay, so to use our analogy, if the particles are just like the black and white balls with hidden variables, their behavior, when tested repeatedly on different axes, can only be correlated up to a certain mathematical ceiling.
Exactly.
But if a real-world experiment shows correlations that smash right through that ceiling...
And Einstein's hidden variables cannot possibly exist. The math proves they can't.
Wow, so those are the stakes. But the experimental proof required to actually test this took decades of technological advancement, didn't it?
It did. The source material highlights a monumental turning point. Alain Aspect's 1982 experiment in Paris.
Right, Aspect.
He used entangled photons, but he added a mechanism that finally tested the absolute core of the problem. He changed the measurement axis of his polarizers mid-flight.
Okay, wait, stop there. Change the measurement axis mid-flight. I want to make sure we really understand the how and the why of this because it sounds physically impossible.
It does sound like magic.
Right, like these are photons moving at the literal speed of light. How do you change a setting while the particle is already moving?
Well, he used highly advanced acousto-optic switches.
Okay.
These switches could redirect the path of the photons in mere billions of a second. So the photons are emitted from the source.
Right.
And while they're literally flying through the air toward the detectors, the switch randomly changes the angle of the polarizing filter they are about to hit.
That is insanely fast. But why is that specific mid-flight change so vital to defeating Einstein's hidden variable argument?
Because of the speed of light limit.
Okay, right.
See, if you set the detectors before you fire the photons, a hidden variable theorist could argue that somehow the two detectors secretly communicated with each other and the photon source beforehand.
Oh, like they coordinated their settings so the photons knew exactly how to act when they arrived?
Exactly. But by changing the settings after the photons are already in the air, aspect created what we call a space-like interval.
Meaning?
Meaning there simply wasn't enough time for a light speed signal to travel from detector A to detector B to warn it about the new setting.
Oh, wow. So if they still perfectly correlate after that.
They're truly acting as a single, instantly connected system, completely defying local space.
So what were the results of Aspect's experiment?
They absolutely violated Bell's inequality. The correlations were far too strong to be explained by hidden variables.
So Einstein was wrong.
Yes, and this wasn't just a one-off anomaly. The sources trace how this was refined over decades. By 2015, we ran tests that closed every conceivable loophole.
The locality loophole, the detection loophole.
All of them. And it culminated in the 2022 Nobel Prize in Physics, which was awarded to John Clauser, Elaine Aspect, and Anton Zeilinger for this exact work.
So we essentially have to throw the whole black and white ball analogy out the window entirely.
Completely out the window.
If I have entangled particles, they are not a white ball and a black ball sitting in boxes. They are like two blank gray spheres.
That's a good way to put it.
And when I open my box and force my sphere to become white, the other sphere on Mars instantaneously becomes black.
Yes. The universe fundamentally allows non-local connections.
I mean, that just totally flips the script on how we see the universe, right? It forces a profound philosophical shift. Local realism is dead.
It is dead. The properties of the universe are not definite, and they are not completely isolated by distance.
Okay, but I have to push back hard here on behalf of human intuition.
Go for it.
Because if local realism is an illusion, right, and the fundamental building blocks of the universe are these fuzzy, non-local probability clouds that don't pick a state until they interact, how on earth does anything feel solid? I mean, I'm knocking on a wooden desk right now.
I hear it.
It does not feel like a superposition. If everything is made of quantum fuzz, why doesn't my hand just pass right through it?
And that is the pivotal question.
Yeah.
How do we cross that bridge from quantum weirdness to classical solidity?
Yeah. How does that happen?
Well, to start, we have to completely unlearn the chemistry we were taught in middle school.
Oh, boy.
We have to look at the atoms themselves, not as rigid objects, but as highly dynamic quantum systems.
You mean the old Democritus and John Dalton model, the idea that if you cut matter down far enough, you eventually hit an atom, which is basically just an indestructible tiny billiard ball?
Precisely the model we need to discard.
Okay.
Dalton envisioned atoms with definite, hard boundaries. But modern physics paints a radically different and honestly almost unsettling picture.
Unsettling how?
Well, we have this fascinating 2024 paper from our sources by Jean-Patrick Conrad. It's titled On Atomic Elasticity.
Right, I read this.
And he argues that atoms are absolutely not solid spheres. They're actually squishy, compressible objects.
This completely blew my mind when I read it, because when I think of compressing something like, I don't know, a piece of wood or a tank of gas, I assume I'm just pushing the hard little atoms closer together, right? Shrinking the empty space between them.
That's the classical view, yeah.
But Conrad is saying the atom itself gets smaller.
Yes. The individual atom actually squishes.
That's wild.
And to understand how, we have to look at what's called the internal quantum vacuum.
No, wait, that doesn't mean like an outer space vacuum, right?
No. It refers to the probabilistic nature of the electron cloud. An atom doesn't have a hard physical shell like an egg. Its size is actually defined by an expectation value.
An expectation value? What is that exactly?
It's the mathematical probability of where its outermost electrons are likely to be found. And that probability is governed by the Schrödinger equation.
Okay, so it's less like a solid jawbreaker candy and more like a swarm of angry bees buzzing around a hive.
That is a much better way to visualize it.
And the size of the swarm is just how far out the bees usually fly.
Exactly. And if you apply extreme external pressure to that swarm, you can force the bees to fly closer to the center.
Oh.
The expectation value shrinks. The atom literally compresses its own internal probability space.
But the sources indicate that not all atoms squish the same way, right? We have soft atoms and hard atoms.
Yes, the elasticity is entirely dictated by the atom's quantum shell structure.
Okay, give me an example of a hard atom.
Helium is notoriously hard.
Why?
Because it has a completely full, tightly bound inner shell, the 1s2 configuration. Because that shell is closed, the electrons strongly resist being squeezed.
So they push back.
Right. And that's why a helium-like ion, such as lithium, is incredibly stable and compact.
Oh, is that why we use lithium in batteries?
Exactly. It's the very reason. Those ions are hard enough to be repeatedly shoved into the microscopic crystal structures of battery electrodes without falling apart.
That makes so much sense. But then you look at transition metals, or heavy elements like the lanthanides. Conrad describes them as soft.
Because their outer electrons exist in much more complex, sprawling orbitals that just aren't tightly bound.
Like a really loose bee swarm?
Yeah, exactly. The radial part of their Schrödinger equation allows for massive deformation. And this leads to a phenomenon under extreme pressure that is frankly mind-bending.
Orbital collapse.
Yes, orbital collapse.
Okay, I need you to explain the mechanics of orbital collapse because the way the paper describes it, it honestly sounds like alchemy.
It does sound
Like you squeeze an element and it essentially turns into a different element. How does that work?
Well, think about the atom like an apartment building.
Okay.
The nucleus is the lobby.
Yeah.
And the electrons live on different floors or orbitals based on their energy.
Got it.
Normally, if you squeeze the building, the floors just get a bit closer together. But under ultra-high pressure, the fundamental energy hierarchy of the atom breaks down. The energy levels of the floors actually cross over each other.
Wait, they cross over. So what happens to the electrons living on those floors?
They fall.
They fall.
Yes. The paper uses cesium as a prime example. Under normal conditions, cesium's outermost electron lives in what we call the 6s orbital.
Okay.
It's a very specific shape and energy level. But if you squeeze cesium hard enough, the energy dynamics shift so violently that the electron suddenly drops into an entirely different geometric shape closer to the core,
Which is
the 5d orbital.
So it just abandons its post and drops into a completely different configuration.
Yep.
And that simple drop changes how the atom behaves in the real world.
It radically changes its chemical properties. I mean, normally cesium is an alkali metal, but when that orbital collapse happens, it suddenly starts behaving chemically like a transition metal.
Wow.
It literally shifts its functional identity on the periodic table purely because it was subjected to physical pressure.
That is incredible. So that must mean classical physics equations, like the ones we use to calculate gas pressure in engineering, they must be fundamentally incomplete if they assume atoms are just hard spheres of fixed volume.
They are incomplete. Conrad argues that classical thermodynamics, like the famous van der Waals equation, completely ignores the nonlinear compressibility of the atoms themselves.
So the math is just wrong at extreme scales.
Exactly. At extreme pressures, like inside the core of a planet or in high-end industrial synthesis, you have to account for the squishy, shape-shifting quantum nature of the atom itself.
Okay, let's step back and look at the puzzle we're building for the listener right now.
Sure.
We've established that local reality is an illusion.
Right.
We've established that the fundamental building blocks, like the atoms making up the desk in front of me, are actually squishy, shape-shifting quantum clouds.
Yes.
So I have to ask again, really hammering this home, why doesn't the coffee cup sitting on my desk suddenly exist in a superposition of being on the desk, on the floor, and floating near the ceiling?
It's the ultimate question.
Yeah, how do we get from squishy quantum weirdness to a solid, reliable reality?
Well, to solve that, we have to look at the work of physicist Wojciech Zurek, specifically his foundational 2003 paper. He tackles what physicists call the problem of Hilbert space.
Hilbert space. That's the vast mathematical landscape where all these quantum possibilities exist, right?
Yes. The principle of superposition says that if a quantum system can be in state A, and it can be in state B, then it can also exist in any mathematical combination of A and B.
Right.
Hilbert space is the realm of all those combinations. So mathematically speaking, a state where your coffee cup is simultaneously on the desk and on the floor is a perfectly valid legal state in quantum mechanics.
Which is terrifying, because I never see that. And Einstein literally pointed this out as a flaw, right?
He did.
He said the fact that things are localized, that they sit in one specific place, seems fundamentally incompatible with quantum theory.
It was a massive paradox for a long time. For decades, physicists viewed the environment like the air molecules in the room, the thermal radiation, the stray photons of light, as annoying background noise.
It's static on a TV.
Exactly. In a lab, if a stray photon hits your delicate quantum experiment, it ruins the superposition. It breaks the experiment.
Right.
But Zurek flipped that perspective upside down. He said the environment isn't just a nuisance. It is an active, vital, witness.
And this witnessing process is called decoherence.
Yes.
Let's break down exactly how this mechanism works, because this is the actual bridge to reality. You call it Ein-selection environment-induced superselection.
Right.
How does a stray photon force my coffee cup to be in one solid place?
Okay, let's visualize the coffee cup in a superposition. It is mathematically hovering in several locations.
Got it.
Suddenly, a photon from the lamp on your desk hits the cup. Now, in physics, an observation doesn't require a human eye. It just requires a physical interaction.
Okay, that's a key point.
When that photon bounces off the cup, it interacts with the quantum state. It effectively measures it.
And what happens to the superposition?
It bleeds away.
It bleeds.
Yeah. The photon becomes entangled with the cup, carrying away a tiny fraction of information about its position. Then a trillion other photons do the exact same thing. Then billions of air molecules bump into it.
Wow.
Every single collision forces the delicate, fuzzy phase coherence of the superposition to leak out into the surrounding environment.
So the environment is just battering it.
The environment acts as an aggressive interrogator. It's constantly bombarding the system, forcing it to abandon its superposition and settle into a robust classical state that can actually withstand the bombardment.
And Zurich calls these surviving states pointer states, right?
Yes, pointer states.
They are the specific states that are immune to decoherence. And I have to say, this leads to my absolute favorite concept in this entire deep dive.
Quantum Darwinism.
Yes, quantum Darwinism.
It is a stunning conceptual leap. It essentially applies the logic of evolution to quantum information.
Right, because in biological Darwinism, the animals with the traits best suited to their environment survive, reproduce, and pass on their genes.
Exactly.
You were saying the exact same thing happens to reality itself.
Literally the same mechanic, but for information.
That's crazy.
In quantum Darwinism, the fittest quantum states are those pointer states, like the definite, solid position of the coffee cup on the desk. They survive the relentless decoherence process.
Okay.
But they don't just survive, they reproduce. They redundantly imprint their information across the environment.
So the reason I see the coffee cup on the desk, and you can walk into the room and see the exact same coffee cup on the exact same desk, isn't because the cup possesses some intrinsic, undeniable classical reality?
No, not at all. You both see it because the environment, the ambient light filling the room, has made millions of identical quantum photocopies of that specific pointer state.
Photocopy.
Yes. The objectivity of our world is measured by the redundancy of those records. We perceive a shared objective reality because we can each intercept a tiny separate fraction of the environment.
Like a few photons entering my eye and a few different photons entering yours.
Exactly.
Yeah.
And we both receive the exact same photocopied information without disturbing the original cup.
That is just staggering. The universe is just aggressively photocopying the information that was tough enough to survive the quantum fuzz.
That's reality.
But, that begs an immediate, practical question.
What's that?
If the environment is constantly bombarding objects to force them into classical reality, how long does that process actually take? Because does reality slowly gel into place, like water freezing into ice, or is it a sudden snap, like boom, it's there?
We actually have concrete data on this now from a very recent 2024 study.
Oh, right, the Barcelona study.
Yes, a team of quantum theorists from the Autonomous University of Barcelona, led by Philip Strasberg, published a paper in Physical Review X tackling exactly this timeline.
They ran massive numerical simulations, right? Trying to literally watch macroscopic structures emerge from the quantum multiverse in real time.
They simulated quantum systems with up to 50,000 interacting energy levels.
50,000?
Yes. Now, to put that in perspective, while 50,000 levels is far, far smaller than a physical coffee cup, it is an absolute behemoth of a simulation for theoretical quantum physics.
I can imagine.
They needed a system large enough to exhibit true environmental complexity to see the exact mechanism and speed of the transition.
And the result, does reality leak or does it snap?
It is an exponential snap.
Really?
The simulation provided clear, undeniable evidence that the vanishing of quantum interference, the death of the superposition, happens exponentially fast as the size of the system grows.
Wow.
You don't need a trillion atoms to create a classical reality. Even with just a small cluster of atoms or photons acting as an environment, the system is forced into classical behavior almost instantaneously.
Which is actually a deeply comforting finding for the listener, I think, because the researchers noted that this process doesn't require fine-tuning.
Right.
The universe doesn't have to perfectly balance on a razor's edge just to give us a solid desk.
Not at all. The emergence of a classical world is ubiquitous and generic.
So it's just bound to happen.
Exactly. Despite the profound, probabilistic chaos of the quantum realm, the mathematics dictate that a stable, classical reality is inevitable. It is baked into the fundamental physics of many body interactions.
It's kind of like statistical mechanics.
Right.
You can't predict the random, chaotic bounce of a single air molecule in a balloon.
Right.
But when you have a billion of them, the chaotic math smooths out into a perfectly predictable, stable temperature and pressure.
A very apt comparison. The classical world we inhabit is a highly robust statistical inevitability arising from microscopic chaos.
Okay, I need to pause our journey for a crucial public service announcement.
Uh-oh.
We have to clarify a major cultural misunderstanding. Because when we talk about decoherence and we say the environment observes the quantum state or witnesses the system, we're strictly talking about physical interactions, right?
Yes.
Because there is a massive subgenre of pop science and, frankly, philosophy that claims quantum mechanics proves reality doesn't exist until a conscious human mind looks at it.
Oh, yeah. It is perhaps the most pervasive and frustrating misconception in modern science.
I bet.
The Wikipedia source on the observer effect in physics addresses this head-on. In the strict lexicon of quantum mechanics, an observation or measurement has absolutely nothing to do with human consciousness, eyes, or brains.
An observation is just a transfer of energy.
Precisely.
Mm-hmm.
If an electron collides with a stray photon of background radiation, an observation has occurred.
Okay.
If a dust mite bumps into a carbon atom, an observation has occurred. The physical interaction transfers energy and alters momentum, which destroys the phase coherence and collapses the wave function.
You don't need a brain.
No. The idea that you need a conscious thinking being to collapse a wave function is entirely unsupported by the physics. Werner Heisenberg himself stated that the observer merely registers decisions, and it is completely irrelevant whether that observer is a piece of measuring apparatus, a rock, or a human being.
Okay, so human consciousness isn't magically creating the universe just by looking at it.
Right.
But, and this is a massive, but just because our minds don't collapse the wave function of the coffee cup doesn't mean biology operates purely on classical Newtonian physics.
Not at all.
In fact, if we look at this groundbreaking 2026 research from Tsinghua and Peking universities, it turns out your biology is fundamentally reliant on quantum weirdness.
This brings us to one of the most exciting frontiers in science, quantum biology.
I love this part.
Specifically, this paper solves a paradox regarding biological ion channels that has plagued biophysics for decades.
Let's ground this for the listener real quick. Ion channels are microscopic pores embedded in the membranes of your cells, right? They act as gatekeepers, controlling the flow of charged atoms like sodium and potassium in and out of the cell.
Right.
They are the fundamental hardware of your nervous system. Every heartbeat, every muscle twitch, every thought you have is powered by ions moving through these channels.
And for a long time, biophysicists modeled these channels using classical thermodynamics.
Okay.
Imagine trying to push a squishy ball through a tight, winding tube. To make sure the tube only lets potassium through and strictly blocks sodium, the channel must have deep potential energy wells.
What are those?
Essentially, they're chemical traps that perfectly fit potassium. But classical physics dictates that if the trap is deep enough to be highly selective, the ion should get stuck, or at least move very slowly.
Which directly contradicts what keeps us alive. I mean, these channels exhibit high flux permeation. They move ions at lightning speeds.
Exactly.
If they move slowly, your nervous system would lag like a bad internet connection.
Right. And when researchers ran advanced classical models like molecular dynamics simulations to predict how fast the ions should move, the models failed catastrophically.
Let me actually read the exact data from the paper because the discrepancy is wild.
It really is.
Classical simulations predicted a conductance of 9.3 picosiemens for sodium channels, but physiological experiments show the biological reality is around 22.0 picosiemens.
More than double.
Right, and for potassium, it's even worse. Classical models predicted 9.2 picosiemens, but the biological reality is a massive 118.6 picosiemens.
The classical models are capturing less than 10% of the actual movement. It's a profound conductance deficit. The math was completely broken.
So what did they do?
Well, the researchers at Tsinghua realized why. Classical models treat the ion as a solid charged sphere, but the constriction point of these channels, the selectivity filter, is incredibly tiny.
How tiny?
It's on the Unobserved scale, less than a nanometer wide.
And when you get down to the Angstrom scale, the physical space is comparable to the thermal de Broglie wavelength of the ion itself. Exactly.
Meaning the ion stops acting like a solid ball.
Right. It stops acting like a particle and starts acting like a delocalized quantum wave.
Wow.
To solve the conductance deficit, the researchers threw out the classical models and applied a non-perturbative quantum transport framework.
Okay, big words. What does that mean in practice?
Instead of calculating how a solid ball bounces over a physical barrier, they mathematically modeled the ion as a probability wave interacting with the barrier.
And what did that reveal? What is the actual biological mechanism?
Subbarrier quantum tunneling.
Quantum tunneling. We hear quantum tunneling a lot in sci-fi. Let's make sure we have a concrete analogy for how it physically works in our cells. Because it's not just like walking through a wall, right?
No. Think of it like a sound wave.
Okay.
If you yell at a thick, solid door, classical physics says a tennis ball thrown at that door will bounce back. It doesn't have the energy to break through.
Right.
But the sound wave of your voice doesn't have to break the door. A fraction of its energy simply propagates through the material.
Oh, I see. Because the ion is acting as a wave packet, it doesn't need enough thermal energy to climb over the chemical barrier in the channel. A low-energy ion can simply bleed its probability wave through the barrier and materialize on the other side.
And the human body takes advantage of this.
Relies on it. Classical physics said only rare high-energy ions could cross. But the quantum framework showed that low-energy ions, which are incredibly abundant at normal body temperature, have a high probability of tunneling right through the bottleneck.
Wow.
When the researchers factored in this tunneling, their quantum model quantitatively recovered the experimental data perfectly. It predicted 21.6 picosiemens for sodium and 119.8 for potassium.
It perfectly matched the biological reality. That is insane. Your nervous system is literally running on quantum tunneling.
It really is.
If your cells couldn't exploit the wave nature of matter, you would die.
It forces a total paradigm shift. I mean, for decades, the assumption in physics was that the warm, wet, messy environment of a biological cell would cause instant decoherence, destroying any delicate quantum effects.
Right, because of all the random interactions.
Exactly. But nature is far more clever. The timescales of this tunneling happen in 3 to 7 picoseconds. The paper notes that this corresponds to intrinsic transport resonances in the terahertz frequency regime.
Terahertz. It's almost as if the biological membrane is tuned to a specific quantum radio frequency just to optimize the flow of matter.
It fundamentally reframes biological cells from being simple mechanical plumbing systems into highly evolved mesoscopic quantum devices.
Which naturally opens the door to some incredibly profound philosophical questions.
Oh, absolutely.
Because if our very neurons, the physical structures that generate our thoughts, rely on fundamental quantum mechanics to function, what does that mean for the nature of the mind itself?
That brings us to the final and undoubtedly most provocative source in our stack.
Yeah, if you thought quantum Darwinism was wild, buckle up. We are looking at a late 2025, early 2026 paper published in AIP Advances by Maria Strum, a professor of material science at Uppsala University.
Now, up until this point in the deep dive, we have been operating under the standard materialist model of physics.
Right.
That model dictates that matter and energy are the fundamental bedrock of the universe. They obey physical laws, they form stars, planets, and eventually, if you arrange enough carbon atoms and quantum tunneling ion channels in complex enough ways, you get a brain.
And that brain produces consciousness.
Exactly. Consciousness is viewed as byproduct, an emergent property of wet meat processing data.
Right.
Strum's paper proposes flipping that model entirely upside down.
Is a massive swing.
It really is. She proposes a framework where consciousness is not produced by the brain. Instead, she posits that consciousness itself is the fundamental field of reality.
Wow.
It is the absolute bedrock layer, and space, time, and matter actually emerge from it.
It is an incredibly ambitious attempt to bridge hardcore physics with non-dual philosophical traditions. Because Strum uses quantum mechanical language to suggest that what we perceive as individual minds are just localized expressions or like nodes of a larger shared foundational field.
Right.
In her model, the material world, the solid disk, the squishy atoms is secondary. It's essentially an illusion or representation projected by this primary field of consciousness.
Exactly.
She points out that major religious and philosophical texts, like the Vedas, used metaphorical language to describe this exact interconnectedness for millennia, and she is attempting to give it mathematical and and physical formalization.
Now, it is crucial for us to state to you, the listener, that we are looking at the source material strictly impartially.
Absolutely. We are not taking sides.
Because, as the source comments and rebuttals vividly demonstrate, this theoretical framework has caused intense, fiery friction in the scientific community.
Oh, the critics are coming in hot, and we have to present their side of the debate clearly, because to many physicists, this crosses a dangerous line.
The primary pushback is about the fundamental definition of science itself.
Right.
A scientific theory cannot just be mathematically elegant or philosophically pleasing. It requires falsifiable predictions and experimental testing.
It has to be testable.
Yes. Critics argue that Strum's framework leans heavily out of physics and into idealism and metaphysics. As one reviewer fiercely noted, if you cannot design an experiment that physically distinguishes the statement matter produces consciousness from the statement consciousness produces matter, then you don't actually have physics yet.
You just have metaphysics.
Exactly.
Well, let me push back on Strum's theory on behalf of those materialist critics for a second, because they raise a devastatingly logical point regarding biology.
Let's hear.
If consciousness is the fundamental field of the universe and the physical brain is just sort of tapping into it, why does physical brain damage reliably and predictably alter personality, memory, and awareness? I mean, if the mind is a universal field, altering the physical meat of the brain shouldn't fundamentally change who a person is at their core. Phineas Gage got a spike through his frontal lobe and his entire personality changed. That implies the meat is the mind.
That is the ultimate tension. And it remains the strongest, most grounded argument for strict materialism.
It's hard to argue with a spike through the head.
It is. Now, supporters of frameworks like Strum's might counter that the brain acts as a filter or a transceiver.
A transceiver.
Think of a radio. If you smash the radio with a hammer, the music coming out becomes distorted or stops entirely. But the radio station is still broadcasting.
Oh, interesting.
The field is intact. The receiver is broken.
Again, to the critics, that's just a clever analogy trying to shield an untestable hypothesis.
Exactly. And that is where the debate currently rests. Strum's framework is mathematically beautiful and philosophically sophisticated.
Yeah.
But whether it is a paradigm-shifting revelation about the nature of the cosmos or just an untestable metaphysical thought experiment remains fiercely contested in the halls of academia.
And I think it's the perfect place to land, honestly, because it reminds us that while we have mapped the genome, split the atom, and photographed the event horizons of black holes, the observer doing the looking the conscious mind itself remains the most elusive mystery of all.
It really does.
Okay, let's bring this all back down to earth and summarize the incredible arc of this deep dive.
We have covered a staggering amount of ground today.
We really have. We started by dismantling local reality, looking at Bell's theorem and aspects mid-flight polarizer switches, proving that entangled particles act as a unified non-local system.
Right.
From there, we zoomed into the atoms themselves, realizing they aren't solid billiard balls, but squishy quantum swarms that can literally shift their chemical identity and collapse their orbitals under pressure due to their internal quantum vacuum.
Then we explore the bridge to the macroscopic world, Zurich's quantum Darwinism. We saw how the environment relentlessly bombards superpositions, forcing them into pointer states. Our solid objective reality is simply the survival of the fittest quantum information, aggressively photocopied by the environment via decoherence.
And Strasberg's simulation showed us this emergence isn't a slow leak, but an exponential, inevitable snap.
Yes.
We brought it into our own bodies, discovering that the ion channels in our cells are utilizing wave packet quantum tunneling in the terahertz regime just to keep our nervous systems functioning, solving the massive classical conductance deficit.
And finally, we waded into the fierce debate over Maria Stremy's proposal that consciousness itself might be the foundational field from which all this quantum architecture emerges. Before we close, I want to leave you with one final mind-bending mechanical fact that ties back to how information flows in this universe.
Hit me.
There's a paper referenced in our sources regarding the delayed choice quantum eraser experiment from 1999. Without getting bogged down in the complex optical setup, the experiment looks at entangled photons categorized into white, gray, and black subensembles.
Right.
What it physically demonstrates is staggering. Quantum interference patterns can be hidden in subsets of data and miraculously recovered later, purely depending on measurement choices made after the photon has already hit the detector and been recorded.
Wait, meaning the actions you take now seem to dictate the state of a particle in the past?
Yes. It mathematically shows that time, causality, and information flow in ways that continually defy our linear human intuition.
Just when you think you have a handle on the rules, the universe pulls the rug out again.
Every time.
And I think that leaves us with a highly provocative final thought, a thread for you to pull on long after this deep dive ends.
What's that?
Think back to that murky, fuzzy X-ray analogy from the beginning of our conversation. If our classical solid reality is just the fittest quantum information surviving through environmental redundancy, and if our own brains evolved to exploit quantum tunneling just to keep the lights on, what immense invisible parts of the quantum multiverse is your brain actively filtering out at this exact second just so you can safely pour your morning coffee?
It is a profoundly humbling thought. The reality we experience every day is not the whole picture. It is just the narrow classical sliver that we are biologically equipped to survive.
Thank you for joining us on this deep dive. Stay curious.